So let me see how far we can get. My goal is to really be able to prove at least a version of the theorem I stated yesterday. So since I'm going to start by restating the theorem and by tell you what I think we have done so far and how we're going to continue. Okay? So let me remind you what the goal was. It was to prove the following thing. So if we have an n-uniform measure, and question 1, n equals 1 or 2, then phi is flat at infinity. I will remind you what this means in a second. 2, if n is greater or equal than 3, there exists an epsilon, which depends on n and m, positive. We live in Rm here. Such that if for every r bigger than r0, and r0 only needs to be somebody bigger than 1, the inf over v that belongs to, maybe I should say something different. For every r greater than 0, there exists a v sub r that belongs to G, so it's an n-plane in Rm. And remember in here, sorry, 0 belongs to the supported phi. And if we have the integral over the distance from x to v squared, br 1 over phi, the unit ball, r to the n plus 2. If this number, if for every r bigger than r0, this is small, then phi is flat. I don't like this blackboard. Okay? So, and what does this mean? Remind you, so phi is flat at infinity means, i.e., the lambda, the tangent of phi at infinity, and I remind you what that means, that lambda is obtained as the limit as r goes to infinity of r to the minus n t0 r. And of course, any multiple of it works also. And any x, so I could put 0, it doesn't matter. Think of it as 0. It means that lambda is flat. And that means that lambda is z0 is a constant hn restricted to a specific v. Okay? So that's what we want to show. The reason we want to show this, so I remind you, is because this amounts to proving that start condition. Okay? So remember, this is enough to show that what I had called start yesterday is satisfied. Let me tell you what that is. Remember, in that case, we had taken f flat. The flat measures m n uniform. And what we had to show is that there exists an epsilon 0 positive such that if dr of phi f, such that if phi belongs to m and this is less than epsilon 0 for every r bigger than r0, then phi is flat. Okay? We're trying to prove this. This is not yet what we really will need to do. To prove this one, what we need to prove, so what had happened? I had, at some point yesterday, I had put this condition on the board. We had agreed that we understood that if I prove this condition, we have everything. We want to prove this condition. To prove this condition, we kind of played with this thing here, and show that if we have this property, then we have this property. And to prove this implication, what the conclusion to my statement here is not then phi is flat at infinity. I would like to say then phi is flat. Then phi is flat. Okay? But that I cannot say yet. And I won't be able to show you that here. I'll just be able to give you an indication of how you go from flat at infinity to flat. But I just want to relate this condition. If we prove these, we're getting closer. Okay? So we want to prove these. To prove these, I will need to be able to write these without this statement here and this statement here. I will give you an indication of how you do that. But at this point, this is how much I can really prove. Okay. Questions? So if you want, this is a summary of where we're going and where kind of we had left things last time. Yes, we had done something else, which I'll remind you in a second. But this is what the kind of what you should think as the goal of today is, and this is why we're doing things. Okay. After I had put all of these, what had we done? We had noticed, I had said, I want to exploit this condition. We had obtained some things. I will remind you I had done it in the ball of radius 1. I'll remind you what it means. And for any ball, I'll write the scaled version. And I also would like to spend a little bit of time, because it's funny. You know, we take this hypothesis, we work with it, we say, well, now we're going to prove everything using these, and you might be thinking in your mind, but this is a different condition. So one of the things I want to spend about a little bit of time showing is that, interestingly enough, this condition and this condition for uniform measures are roughly equivalent. Okay? So that to mean that once we drop this condition and we only work on these, we haven't missed a lot. We actually are talking exactly about the same sort of measures. Okay? Questions? Okay, so here it is. Here's what happened. So after we started playing with that condition over there, let me call it, I don't want to call it 1 because today the numbers are going to matter. Let me call these double star. Okay? Once I started working with double star, let me tell you what we were able to prove. We showed that using double star, we were able to prove the following. That for every tau bigger than 0, there exists as epsilon 0 positive, such that if phi is n uniform, phi of the unit ball is 1. And you know what? Let me call these double star epsilon 0 so that you keep it in mind. And double star epsilon 0 holds. Then the Hausdorff distance between the support of phi intersection BR. So then there exists V sub R. Actually, it was the same one that we have there, but and V sub R intersection BR is less than tau R. So we had proved these with R equals to 1. I just rescaled everything, and this is what we obtained. Okay? And what is the Hausdorff distance? Let me tell you what this is. This tells you this is the sup, actually. So let's make Guy happy. This is the sup over the y that belongs to the support of phi intersection BR of the distance of y to VR plus the sup of y that belongs, and maybe I need a 2, it doesn't matter, that belongs z that belongs to VR intersection BR of D of Z support of V. Okay? This is more or less that. So remember, we had proved that double star epsilon 0 told us that this was small, and then we had proven that there were no holes. Okay? You're awfully quiet. Yes? Oh, yes, yes, yes. Yes, always for every r bigger than r0. Okay? And if you think of it, what this means is this is a plane. Okay? What this is simply a rectangle, or in codimension water, a cylinder of width at this radius tau r. And what this is telling you, so what this, the picture of this r is very big, okay? This is telling you, if this is r, and this guy is VR, what this is telling you is that when you look at this tau r, so tau r is small, but r is big, so everything is a scale thing. So this is 2 tau r, and that is telling you that the support of the measure here is somewhere here. So that's the first piece. The second piece is telling you that there's no holes, okay? That if you were to do a rectangle that's parallel to this wiggly thing, the whole plane would be in there. Okay. I want to make one remark, is that the same way that we proved this yesterday, we could have proved that this also implies that FR of phi over so maybe I'm not gonna phi over I guess I need to divide it, FR of phi, and a constant Hn of VR. So I'm not going to write is also less than tau. Okay. What do I want to say? I want to say that by choosing epsilon 0 small enough, not only can we make this small, but the same argument. Same argument means you do another contradiction argument and stuff like that gets you this. Why did I write that? Because I want you to think, out of here, out of this condition, by manipulation we got to something like this condition. What I am claiming, that out of this condition and the fact that phi is n uniform, I get back to this condition. Okay? This condition, if this is small, then dr is small. So the two things are equivalent. So I haven't lost anything. For the n uniform measure being close to the flat measures from some point on, can be written in terms of this complicated measure or in terms of the beta 2 being small. Okay? I want to emphasize that's only true for an n uniform measure or for the measure along those lines. Okay? Some additional conditions are necessary. So what's the advantage? I'm going to forget the FRs. I'm going to forget the DRs. I'm only going to focus on the condition double star. Questions? Hey guys, this is a really good time to ask a question, because now things are going to, this is supposed to be a recap, now things are going to start happening. Okay? Okay. Now let's stare what I have on the board states something about the tangent measured at infinity. Okay? So before I start doing my computations, and I promised I was going to compute things today, and I will compute things, because at some point, I mean, one of Price's argument includes a number of computations, a number of moments. I want to give you a flavor. I'm going to give you the not scary flavor of it, not the scary flavor of it, but we will do some computations. But before I do anything, I would like to translate my condition double starred epsilon 0 into a condition about lambda. Because if I'm going to prove something about lambda, I better understand what on earth that condition says about lambda. OK? So what's lambda? So let's stare at that. And let me remind you, so lambda is the limit. It's over there. R to the minus n, let's assume the x that I'm choosing is 0, t0 r of phi. So that means I need to scale this condition. OK? So let's assume that phi of b1 is 1, so I can drop that. And I want to write, so I want to understand what these mean. Distance of x vr square d phi. Well, this is the same thing as the integral over b1 of the distance of z r to the minus n t, vr, because when you scale this plane, you get a plane, r to the minus n, so let me write it like that, d r to the minus n t0 r of phi. OK? This is the same thing as this one. I just did a scaling. Do a change of variable, write x as z over r, and you do that, and that's what you obtain. OK? I scaled everybody. And what I'm assuming is, OK, and you agree this is a continuous function. Yes, it depends on r, but this one, for every sequence going to infinity, this converges. So as r goes to infinity, if this is less than epsilon 0, so letting r go to infinity, you believe me that this gives you b1, that there exists a v infinity such that the distance squared of z to v infinity d lambda is less than epsilon 0. So this condition, you see why I needed it for every r bigger than r0, so I can really go to r going to infinity, tells me this. OK? So now I have gotten rid of phi. I have a condition on lambda. I want to prove something about lambda. OK? So this is what I have to work with. OK? And yes? It doesn't matter. Yeah. Since I can play with my lambda, my epsilon 0. If you want, put a strict in the first one and put it. So what I'm going to do is I'm going to rewrite. Maybe I won't rewrite it now. Let's just reread it. So the theorem on top says, I'm rereading. If phi is an n uniform measured, n equals 1 or 2, then phi is flat at infinity. And then for n greater or equal than 3, what I'm going to prove is that if I have this condition on the tangent at infinity, then this measure is flat. Okay? So let's try to understand. Let me remind you for a minute, lambda is n uniform. So what we're going to prove, and the other property I have at lambda is that if z belongs to the support of lambda, tz belongs to the support of lambda, okay, for any t positive. So what are we really going to show? Here is what we're going to show. We're going to show that if you have a measure lambda that is n uniform and is supported on a cone, this is what this tells you, that lambda is supported on a cone. You have an n uniform measure supported on a cone, and over there at infinity, it approaches a plane. It has to be a plane. You cannot approach a plane without being a plane. Okay? Does that make sense? That's what we're going to prove. Okay, so we need to prove that lambda is really modulo rotation and translation is Lebesgue measure on Rn. Modulo a constant, but that doesn't matter. Yes, you have a question.
Yes, not probably a big question, but I don't remember why it's obvious that lambda is a uniform.
Oh, because it's so. Well, the reason you don't remember is because I never explained. Okay, I said that tangent measures to tangent measures were that the tangent measures every time the density existed gave you an n-uniform measure, and of course I only took R going to 0. Okay, but so the cheap explanation is you agree that this one phi is a uniform measure. Okay, this one is also a uniform measure. Okay, let R go to uniform measure means how much balls measure. Let R go to infinity. For almost every ball, you will obtain that lambda is like R to a power. Okay, and you'll see that you can do it for every lambda. Okay, so the same argument I use to prove that when you blow up a measure with density, you go to an n-uniform measure can be used to prove that this one is n-uniform. Okay, I never said that. Okay, thank you. Okay, so if you're n-uniform and you live on a cone, and at infinity you look like, at infinity you can be squeezed in a cylinder, then you have to be flat. Okay, so that's what we want to show. I'll remind you of that. Now we're going to compute. Now we're going to do a computation. This was a computation that Kowalski and Price did. So when they were trying to understand who the n-uniform measures were in Rn plus 1, they did, so the paper, as I think I had mentioned, has 2 parts. So Kowalski was a differential geometer. Price did GMT. So the paper has 2 parts. A first part of differential geometry, a second part in GMT, and a part at the end where they put everything together. Okay? So what does that, so what the differential geometry part of that paper says, you have an n-uniform measure in Rn plus 1. You know that you have lots of smooth points by Kurtheim and Price. You decide you're going to do at one of these, so you have a smooth point. At that point, you look at the support of a measure as a nice manifold, smooth manifold, and you do a tailored expansion for the volume. Okay, and you do lots of, you write your manifold as a graph. That's where you use the codimension 1. The graph of a real valued function is way easier to understand than the graph of a vector valued function for higher dimensions. So you do your computation, and you obtain that the volume can be written as has a tailored expansion. Since the volume is exactly equals to something, the first term, it means all the coefficients in the tailored expansions have to be 0. The first coefficient that you look at tells you something about the curvature of the manifold. The second one gives you something about, this is second order PDE on the curvature of the manifold. You analyze that and you get some information. Kowalski. Price said, okay, now, I mean, I don't know, I really don't know how they did this work, but looking at it, that's what one has the impression. Then Price said, I have an n-uniform measure. It means that the integral of all rotationally symmetric functions are the same. Remember, he had done something like that in the work with Kurtheim. I know that the thing lies on the 0 set of a real analytic, or the intersection of real analytic functions. Maybe I can get more information. Okay? And so here it is what they were able to do, and this is what we will show. So I want you to see the statement, and I want you to be ready for the computation. Okay? So theorem. And they were able to do it. You do this computation, and we're going to do this computation in any codimension. They were able to use it in codimension 1 for good reasons, But we will be able to use it in all codimensions. Okay?
By the way, did you finish the proof of the theorem?
Of this? No. I'm actually going to present a piece of the proof of that. I'm going to present the proof of that theorem. When I replace, I am going to show that if this happens, then lambda is flat. No. I will hopefully finish that by 11:30. Okay? Let's hope. No. Many things are going to happen between right now and the price. Okay.
This present theorem you are going to show us is related to that previous theorem, or is it separate?
No. The theorem I'm going to present here will allow me to do a calculation that will allow me to prove this little arrow here. Okay? So, sorry, maybe I should have made, from now on, everything I say until the moment I write theorem, the theorem I'm going to prove, I'm building on the tools. Sorry, I need to put the tools somewhere. I'm going to put them here. Okay? I know it's a theorem. I mean, there are lots of tools. Okay? It's not, okay. So, but this is about any n-uniform measure, not only lambda. Okay? N-uniform. Okay. In Rm, we assume that 0 belongs to the support of phi, and so that my numbers, because I'm going to decide that the measure of a ball is, I decide 2 to the n, r to the n. Why did I choose the constant 2? Because I have done these computations many times in different contexts. I always put 2 there. If I don't put 2, I'm going to mess up every single constant from now on. So there's a 2. Okay? If you prefer 1, you divide all my constants at the end. Okay? But I like 2 today. Okay. And so for every x, okay, so that's for every x and every n. So then there is a degree 2 polynomial. We're going to call it P, such that the support of phi is contained in the 0 set. That means if you are the n-uniform measure in Rm, you live on a quadratic. Why was this good enough for Kowalski and Price? Because if you're in codimension 1 and you live on a quadratic, that gives you the equation. There you should be able to figure out who you are, and that's exactly what they did. They figured out who they were. Questions? Okay, here is the calculation of the week. I need everybody to, I guarantee, even if to this point, by now, all of these measures are making they're swirling around, and you feel that you have been, in a merry-go-round, and everything is getting shaken, and you cannot make heads and tails of where on earth you are. I guarantee the computation I'm going to make, I could be doing it in a calculus class where students understood Fubini. Okay? So everybody is able to understand this computation. Everybody will be able to get something out of this computation, but we just need to focus on the computation. Okay? I'm not going to do anything other than using the definition of the inner product and Fubini's theorem. Okay? Guaranteed. Okay.
So this polynomial is doesn't homogeneous, just linear or linear.
You're killing the suspense of my story.
Sorry? Yeah.
You're killing the suspense. So what's going to happen? Okay. If you get bored, it's Josh's fault. Okay. So what's going to happen is, as he pointed out, for a uniform measure, I don't get a homogeneous polynomial. Okay? I get a polynomial of degree 2. Given the fact that 0 belongs to it, it's not going to have a constant, but that's Now, the beauty of this story, the thing that's going to allow me to show you something, is that when I have one of these measures which are homogeneous, I'll be able to prove that my polynomial is homogeneous of degree 2. And because the polynomial has a structure that relates deeply to the geometry of the measure, I'll be able to read everything out of the measure. Okay? So that's why. But in general, it's not. Okay? And the magic of Price's work is to prove that in the case where you are flat at infinity, you have a homogeneous polynomial of degree 2. It's homogeneous. Okay? But okay, if that comment was above, that comment was not intended to be made here because that a calculus student will not have understood that one, but I'll go back to it. Okay? Okay, so ready. So we are going to use the moments. So Price used all the moments. We're only going to need the first and the second moment. I remind you, the first day I talked about the first moment. I said it was the center of mass. I need to modify my center of mass a little bit so it scales correctly for what I'm going to do. So I'm going to define two moments, the first moment and the second moment. The first moment, and I'm already seeing a problem here, but okay, is B sub r is n plus 2, 2 to the n plus 1, r to the n plus 1, the integral over br of r squared minus y squared, y d phi y. Okay. And it's already looking like I made. Yes, ay, Tatiana. I have this funny feeling that I might need a 2 here. We'll see. Sorry. I think, bear with me. Well, I have a 1. I have a senior moment there. I believe it's a 2, but we'll see. And q of r of x. So this is the second moment. Is n plus 2, 2 to the n, r to the n plus 2. No, this has to be a 2. Sorry, it's my skin. Still doesn't. BR d phi of y. Okay? What's the first moment? Is a linear map. Is roughly the center of mass where I have weighted by this little thing over here. What is this? This is a quadratic form somehow associated with my measure. Okay? Okay. 0 belongs to the support. This is the thing. Let's start looking at the properties of this. What can I say about q sub r? So this is going to have the number 1 today. Q sub r is a quadratic form, and q sub r of x, well, it's easy. I can replace x squared. I have a y squared that I depend by r squared. If you look, I arrange the numbers, so this is less or equal than n plus 2 x squared. For every single r, this is a bounded quadratic form. Okay? I just put a, just take the, this is x squared, this is bounded by r squared, and the measure of this ball is 2 to the n, r to the n, and that's what I get. Okay? So far, nothing has happened. Let's compute, let's understand this quadratic form. Okay? So, this quadratic form, you know that quadratic forms can be written as the sum from I, j, from 1 up to m. Remember, we live in Rm. Ai, j, r, depends on r. xi, xj. Okay? That's a quadratic form. The ar, ij's, r are something. And we are interested in looking at the trace. The trace of q sub r, so this, I should write trace because otherwise everybody. This is nothing else than the sum from I equals 1 up to n of AIIR. And let's compute that. So that's the sum from I equals 1 up to n. So the ii's, well, corresponds to n plus 2 over 2n r to the n plus 2, the integral over br. And so this is when I have AII, that's when I have the xi squared. And so that's yi, maybe, sorry, that's better. Yi squared dphi. Okay? And what's that? That's nothing else. The trace of q sub r is the same thing as this n plus 2, 2 to the n, r to the n plus 2, the integral over br of y squared d phi y. Okay? Does that make sense? And now we compute. And I'm going to do the computation because I'm going to obtain, there's going to be a, I'm going to give you a number here, okay? And I need you to believe that that I didn't lie, that, I mean, you get a number, okay? So this is n plus 2, 2 to the n. Is that the number is too good to be true if you haven't seen it before? Is the integral from 0 to r squared of phi of the point y, where y squared is less than r squared, but bigger than t. dt. And let me finish the computation over here. So the trace of q sub r is I have nn plus 2, 2 to the n, r to the n plus 2, and I have this integral. Okay, and the integral is the integral of this number, the ball, that's an annular region. We have a nice measure. The measure, that is 2 to the n, I put a 2 to the n there, is r to the n minus t n over 2 dt. And now I know you can do this one, and it gives you n. So the trace of q sub r, no matter who r is always n. It's a number, very nice number. Okay, I need to produce a quadratic polynomial. Okay, somewhere here says that there's a quadratic polynomial. To produce that quadratic polynomial, and I'm having serious Blackboard issues, I need to find the quadratic polynomial is going to come from the relationship there is between b sub r, q sub r, and something else. Okay? So I need to be able to do that. And here we go. Yes.
Why we have n always is because the measure is uniform?
And uniform, yes. Because this, if you think of it, this is nothing else than phi of the ball of radius r, but phi of the minus phi of the ball of radius square root of t. And that's how I got that numbered over there. And that's what I have. Yes? Exactly. All the computations are exactly the same as computations are in Rn. That's part of, there's a theorem in Price that says any radially symmetric thing is basically the same as Rn. He has a little bit better, even more is true. Okay, as we will see, but I won't quote that. No, this computation is the one that's in Rn. Yeah, exactly. But it does not only works for radially symmetric function, it works for a little bit more general functions. And I'm trying to figure out what to do, and I think I'm going to do something horrible. I will rewrite some things because otherwise, but is that, I need to have a lot of room space. So let me tell you what I will rewrite who the moments are then. Sorry. So remember, phi is an uniform, BR, and again, let me get my constants correct, otherwise it's a pain. Sorry about that. Q sub r of x is n plus 2, 2 to the n, r to the n plus 2, br x y squared d phi. And what we have proven so far is that the trace of qr is n. Okay, that's where we are. And I had something else that I called 1 that I need to keep. qr of x is bounded by n plus 2 x squared. Okay, that's where we are. Okay, bear with me. I guarantee everything I'm about to say is not complicated, but it's also needed. Okay, so I take an x in the support, and I take it with radius less than r over 2. And I'm going to define 4 balls. Okay? B1 is the ball of center x and radius r. Let me make sure B2 is the ball of radius r and center 0. Oh, no, sorry. Already B1, sorry, is x, r minus x, norm x. B2 is the ball of centered x. B3 is the ball of centered x and radius r. B1, centered x, radius r minus x. B2, br. B4, something tells me these are not correct. Sorry, let me think for a minute. Right, Tatiana. Okay, sorry. 0 and 0. Okay, so B1, what am I trying to do? I am trying to, and I hope x over r minus x. Sorry. No, sorry about that. I don't want to make a mistake here. That will be deadly. Here is an x. Okay. Okay. So I choose 4 balls. Ball of centered x, radius r minus x. The ball of radius r, center 0, centered x and radius r, centered x, r plus x. Okay? What do I notice about these balls? Where their ones are included in the other ones. So B1, so let's see. B1 is included in B2, okay? And B2 is included in B4, okay? Just by. And now B1 is also included in B3, if I'm not mistaken. Yeah, that's obvious, and is included in B4. Okay? This, maybe I should draw a picture. 0, x is here. X is here. And I log that ball of radius r minus x, so it's going to be somewhere in here. And then r plus x is going to be here, and the other one, so I don't know if this is clearer or more confusing, but. And r plus x is somewhere in between here. Okay? Somehow. And I'm going to call j sub I the integral over bi of r squared minus x minus y squared d phi y, squared here, d phi y. Okay. Let me take a pause and try to remember, I need to produce a quadratic polynomial. The only way I know how to produce quadratic polynomial is by looking at these things square. Okay? Let's go back to when we talk about Marstrands. Let's go back about there we wanted to get information. If you want first order information, what happens linear, in the first order. So we use an expression like this. Here we want to get information about the first order and the second order of this measure, the quadratic part. We need something like this because we are going to get what happened in Marstrand. In Marstrand we had the inner product of anybody on the support times a vector was less than a quadratic, and we got information out of that. By doing this, the way we're going to produce that polynomial is by saying we have a linear combinations of things that have polynomials, linear parts and quadratic parts is going to be less than a cube part, and I'm going to get information out of that. Okay, so I need to put more than quadratic to get the information. So let's see what happens. So now I'm going to do a little bit of algebra. What happens if I take a point y that belongs to B4 minus B1? So B4 is this x r plus x and x r minus x. I need to understand the following number. Well, maybe before I do that, let's just there. So with these inclusions, what can I say? Well, I can say that if I look at what happens, J2, which is the ball here, minus J3, okay, I'm integrating in these two balls. This is going to be less or equal than the integral on J4, just because of the inclusions of the ball, minus the integral on J1. Okay? There's nothing complicated, it's the balls. And now what I would like to do I'm going to compute J1 J4 minus J1, and I'm going to compute, and when I say compute, I mean compute and estimate J2 minus J3. Okay? So I need to start here. What's that? Is the integral of this function in B4 minus the integral of the same function in B1. Therefore, I need to understand how big this function is there. Okay? So let's take a point y that belongs to B4 minus B1. And remember, I'm trying to understand this function. Therefore, I need to understand x minus y. So x minus y there is going to be less than r plus x. This is not rocket science. This is less than r minus x. I'm just writing what it means to belong to that function. And now I do r squared minus x minus y squared. And that's going to be less than 2rx minus x squared. And then this is going to be less than minus x squared minus 2rx. And when I square them, or when I put an absolute value before I square them, this is less than, remember x is less than r over 2, in particular less than r. This gives me less than 3rx. Why did I do that? Because now I have an estimate for G4 minus G1. Look, G4 minus G1, which is the integral over B4 minus B1 of the function r squared x minus y squared squared d phi. What this tells me is that it's less than 9r squared x squared, okay, because I have to square it, phi of B4 minus B1, and B4, and so I said that's 9 r squared x squared 2 to the n. Phi of B4 is r plus x to the n minus r minus x to the n. Okay? And what that gives me is an x cubed. So what I obtain here, let me put it in a box. I need a box. J4 minus J1 is less or equal. Then if you compute that, it gives you an 18n, this is irrelevant, r to the n plus 1 x cubed. I don't care about 18n. 18n is a constant that depends on n. I care about x cubed. I really care about x cubed. And I care about rn plus 1 very much. Okay? Questions? Yes? Who is Q? Oh, Q is 9. Well, yes, that Q is a 9. Okay. Okay. Okay, so I have no idea who this is yet, but I know that it's bounded by a cube thing times Rn plus 1. Now we need to compute J2 minus J3. Okay, so J2 minus J3, we might think that is a little bit more complicated, but so J2 was BR of r squared minus x minus y squared d phi y minus the integral over b2 bxr r squared minus x minus y squared d phi y. Okay, and u is what a mess. But we are going to, exactly as it was pointed out, any computation of a rotationally symmetric thing is as a computation in R. Same thing we did for mass trends tells us that this thing over here, which looks so scary, is nothing else than BR, r squared minus x minus y squared. I say it looks scary because now we have two different balls. This is not rotationally symmetric anymore because the center here is 0, it's shifted. But what we're going to do is say, well, I'm going to change these as the integral over BR of r squared x squared, sorry, y squared d phi y. Okay, this is the same computation we did with Marstrand. This is a rotationally symmetric function centered at x on a ball of centered x is the same thing as the same rotationally symmetric function at a different point. Okay, I'm not going to do that. And now, and I'm, no? Okay. Remember? It's okay? Okay. So? Why is this guy the same as this one? Because if you think of it, so this is a radially symmetric function. So I have two options. Either we do the calculation, and I say this is bigger than t, and this is, when we expand in Fubini, this is going to give me the measure of a ball at the of centered x and some radius that depends on t. But x is in the support, and 0 is in the support. And this is the ball of center 0 and radius r. So that's why it's the same. Okay?
Thank you.
Mm-hmm. Okay. And now, and this part I'm sure you can do. Okay, so this is painful. You have a squared, you span the square. So you span every square. You span this square. Let's think what it gives you. It gives you an x squared. I'm not going to do it, okay? But it gives you an x squared, a y squared, and an inner product. You proceed to square it again. So it gives you the R4 here. Check it out. It goes away with this R4. You get y4 here, goes away with this y4. Now you're going to get a double product. So you're going to get something that has an x times y squared. You keep it. Okay? And then you're going to have a double product, a finite double product of something that has x. So you're going to have x dotted with y times an x squared. That gives you an x cubed. You put it in the garbage over there. It's not garbage, actually. It's very useful garbage. But so it's not garbage yet. It's recycling. Then you have an x dot y with a y squared, and you have an x dot y with an r squared. X, my first moment. You have an x dot y, look at the first moment over there. I have an x dot y with an r squared, and x dot y with a y squared. Starts looking like a br dot x. Okay? You believe me that if you clean up all of these things correctly, here is what you obtain. Okay? So this is just a computation. So I'm just going to tell you what the result of your computation is. I am going to keep the recycling for a minute so that you see what I do with it. So I told you we have a BR, r squared minus y squared times xy d phi. Okay, that one you believe me. Plus a 4 BR xy squared d phi y. Of course, I'm keeping the things I like in front. I always minus 2 x squared BR r squared minus y squared d phi y. So these are the terms I cared about. Here comes the recycling. Plus x4 phi of BR minus 4x squared BR xy dpy. Okay, let me tell you why I put some in white and some in orange, and why I cared about them in different ways. Let's stare at each one of these terms. Don't worry, and I haven't forgotten, I'm going to give you a break. You look at this one. Okay. If I divide by the correct number, I mean, forget divide by the correct number. This guy looks related to BR. Is that correct? Look, you have an r squared, a y squared, y d phi, and you're just multiplying it by x. I know the scaling is not correct. Don't worry about that yet. Now, xy squared. Xy squared is nothing else than, look, it's kind of the term that appears in QR. Let's start at this term. I have a 2x squared, and then I have this number over here. This is the integral over BR of r squared minus y squared d phi. This piece doesn't have an x. This piece is a constant. The same way that I computed the trace, I can compute these. Okay? So think of it. This is r squared d phi minus the trace is going to give you something that has an n in it. I mean, yes, there's. Okay, so what do I do now? Oh, and then let's look at the orange numbers. So the orange thing, this is an x4 r to the n. And this gives me, this is a BR, and this gives me an x3 r to the n plus 1. And that's my, where did I put my garbage? Don't tell me I erased it. It's here. Okay, so that's of the same order that the thing I have afforded to put on the right-hand side. Okay, so I am going to write the terms I cared about for BR r squared minus x minus y squared. Don't worry, we're almost at the point where giving you taking a break is a good thing. Just a minute. Plus 4 BR xy squared d phi minus 2 x squared BR r squared minus y squared d phi. This is all bounded by a constant depends on n, r to the n plus 1 x cubed. I'm not going to, do I tell you? Yes, I'm going to tell you apparently. I'm going to tell you who this number is. I'm not going to compute it. Now you know how to do it. You're experts at it. This number is exactly 2n plus 2 r to the n plus 2 over n plus 2. And you should be super happy because A, the break is approaching. 2, this number here is the inverse of that one, the thing that appears in front of the QR. So when I divide by this number, check out what I get. So divide now by this number, okay? Here is what you obtain. You obtain 2 BRX plus QR x minus x squared is bounded. I divide by Rn plus 1, so and a constant, Cn x cubed over R. Okay? I just did. And this is a very good place to take a break. Okay. So when we come back, we'll use this thing. So what happened in the first part? I did a very long computation to get somewhere. So what happened in the first part is I put this condition that told us we're close to a plane. I forgot it. I did a computation. I get this quadratic form. And so now I need to use these. And I need to understand what the relationship between the quadratic form and being close to a plane is. Okay? So I am at the box 5. Okay? I want to say simply because there was this question the first time about whether there were conditions that guarantee that your tangent measures that your measures are flat. I would like to point out that if it had been in the situation where the measure is not only n uniform, but for every x in Rm, the measure of the ball is less than r to the n, forever I will have here, without absolute values, an inequality for every x. And it's out of there that you get additional information. I had thought that if I had time, I will do that. I don't, but I just wanted to indicate if you're interested, that's where you can go. Okay, but I have the box. So this box holds for every x that belongs to the support of phi, where x less or equal than r over 2, and every single r positive. Okay. Q is somewhere else. Yes, up there. Great. I let r go to, and this constant only depends on n. I let r go to infinity. Okay. Oh, and I erase. Don't erase, Tatiana. I let r go to infinity. I have a really nice r goes to infinity. This goes to 0. R goes to infinity. This is a quadratic form which is uniformly bounded. Given a subsequence, converges to something. So given a subsequence, it converges. Okay? So this converges q sub r for some sequence Ri going to infinity. This converges to a quadratic form q, and the trace of q is n. Okay? And I would like to, okay, well, let me not say that. Okay, let's stare at B sub r. B sub r is over there. B sub r, I claim, so this converges, 2BRX converges also. I need to show, and I'm going to wave my hands a little bit, B sub r belongs to the support. Without too much effort, you can prove that B of Ri also converges to somebody. Okay? And therefore, you obtain that for every x in the support, 2bx qx minus x squared equals 0. Let me point out that the trace of this is n, the trace of this is m. Therefore, this is a truly quadratic polynomial, of degree 2. This is P. Okay? So it's true that if you are the support of an n-uniform measure, you live here. Okay? So this is my quadratic polynomial, trace of Q is n. And let me leave it. Now I want to do two things. Remember, we're going to prove something about lambda, the tangent measured at infinity. And lambda had the following property. Okay, so now I want to apply this to lambda, which is n-uniform and supported on a cone. So such that if x belongs to the support of lambda, tx also belongs to the support of lambda for every t positive. Okay? So take a z that belongs to that support of lambda, intersection Sm minus 1. And now, since z belongs there, tz for any t belongs, I'm going to plug in this for tz. It tells me that 2, so tz belongs to the support of lambda, and I apply that here. I know it's a different, but I want to. Tz plus 2. This is quadratic. I have a t squared in front. Qz minus z squared equals 0. So I am applying what I know for n uniform measures for these special ones. And I guess you're not seeing any. Okay? This magic, t squared t. I divide by t. Equals 0. And letting t go to 0, I prove that for every, so what do I have? Let t go to 0. And I prove that 2bz is 0 for every z that belongs to the support of lambda and Sm minus 1. But since it's a cone, this tells you that 2bz is 0 for every lambda, for every z in the support. And so what this is, it tells you that in this case, the support of lambda is not only is included in the following quadratic polynomial. Okay? Qz minus z squared is what Joshi had asked. If you are the cone, if the support of your measure is a cone, you are inside a homogeneous polynomial of degree 2. Questions? Yes?
Can we say something more about that convergence? Because in one hand we have a polynomial of degree 2, and in the other hand we have a polynomial of degree 3.
But because what we let converge is, I let r go to 0. So the answer is yes and no. Okay, let me explain why I mean. So in this situation, you never use the fact. For this purpose, you don't. In other work I had done, which I had thought if there was time I was going to talk about, but that won't happen, when rather than looking at whether, so one of the takeaways from this course is that the density ratio, the behavior of the density ratio, the measure of the ball of radius r over r to the n, gives you information about the support of the measure. You might be wondering to what extent it gives you also classical information. So if this density ratio were approaching your limit at a power rate, you would like to know whether you have smoothness of your support. Of course, you cannot because there's a cone, but do you have smoothness in some sense away from a bad set? The answer is yes. How do you do that? Well, you study this and you obtain this cube here and you obtain an error term. And for that sort of thing, yes, you use very heavily the fact that you have a cube here and that this is a square. Okay? So the bottom line is that having, in cases where you don't have equality but you have almost equality, using the fact that you have a cube here and possibly an error that you can control allows you to do some sort of, you cannot blow up, but allows you to do some sort of multi-scale analysis that gives you information about the support of the measure. But I'm not going to go into it. So that's why the answer is both yes and no. Okay. Okay. So now we are there. And now I would like to state, so where made my, maybe I should state the theorem I want to prove. Okay? So. And you understand this theorem amounts to proving the theorem we had over there. But so, theorem, here is what we're going to prove. Let's assume lambda is n-uniform, but is conical. And for every t positive, if z belongs to the support of lambda, then tz belongs to the support of lambda. Then 1. If n equals 1 of 2, lambda is flat. I will not do this. This works the same way as the one I'm going to do. I'm going to do this. There exists an epsilon 0, depending on n and m, such that if the integral, and let's assume, so 0 belongs to the support of lambda, and let's assume that lambda of b1 is 1. It doesn't matter. I mean, I just need to fix it. Distance of x to v squared d lambda is less than epsilon 0 for some v. Remember, this was the condition. So when we assumed that phi was flat in that funny sense and we took the tangent at infinity, this was the condition that the tangent at infinity assume. Then lambda is flat. Okay? So I'm not going to prove that all of the n-uniform measures which are flat at infinity are themselves flat. I'm just proving that the tangent measured at infinity is flat. And for the comment I will make at the end, and would love you to remember, if you could remember this. Okay, so ready. We are basically done. Okay? And let's see why we're basically done. So what do we know? So we know that this guy supports here. We know that the trace of Q is n. And if you remember how Q showed up, Q was a symmetric form. Therefore, I can diagonalize it. I assume it's diagonal, so I diagonalize it. So let alpha 1, alpha 2, alpha n, alpha m. It was a positive, a non-negative symmetric form, so it's the eigenvalues are greater than or equal than 0. And the eigenfunction, the eigenvectors are ek, k from 1 up to n. And I would like to remind you how it was obtained. If you remember, my q sub r still is somewhere up there. And then I let r go to 0. But remember, this is for the. Now let me write q sub r. If you think of q sub r, not for the phi, but for lambda, remember it's a cone. So whatever I have at the ball of radius r correctly scaled is the same thing. So let me write q for lambda. Okay? So this is the q written for lambda, q of x. Yes, at the radius r is that, but it's the same thing at any radius, so because it's a cone. Remember, maybe I should emphasize the fact that we are a cone here tells you that lambda Ta is t to the n lambda of a. And so this is 2 to the n, the integral over b1 of xy squared d lambda. Okay? And so this is the q that shows up here. Okay? What on earth is the inner product? I'm going to write this a little bit different, hopefully to emphasize what I want to emphasize. This is the integral over b1 of xi y. Remember, I am using now, I'm going to write x and y in these bases. So what I have here is the sum of alpha I xi squared plus I equals n plus 1 n plus m alpha I xi squared. Okay? I just wrote it. And there's an integral, and so my integral, my 2 to the n, went away. Sorry. If I'm not mistaken. Let me assume I have a constant of n and I don't worry too much. Okay? Yes? Up to m, sorry. And, huh? No. This is just the indices. I start from 1 up to n. I just divide it into 2 pieces. We don't know if we have an eigenvalue equal to 0. A priori, actually, I'm about to show you that we have n minus m, but just a second. Okay, so this is what Q looks like. And my hypothesis says how do you measure the distance to a plane? This is 0. You measure this by doing the inner product with the orthonormal vectors. Okay? The fact that I have a plane, n plane, such that when I look at this distance, which amounts to doing, imagine what this is. This amount, let's assume we were in codimension 1 for a minute. This will be simply this distance squared. What this is telling you is that this distance squared is small. Okay? So what I claim is that by the way you construct eigenvalues simply by applying to the quadratic form and dividing by a squared and minimizing, what this tells you is that this piece over here is small. The V that we have there is not necessarily the same V that allow the one that's spanned by En plus 1 all the way to En, but they're not too far. Okay? So what I claim is that what I had called double star, and I'll leave you, double star implies that, and remember, this xi squared is in the ball of radius 1, so that's not. What this implies is that the sum from I equals n plus 1 up to m of the alpha i's is small, epsilon 0 prime. Okay? Okay. And remember, what am I trying to prove? I'm trying to prove that lambda is supported on a plane. Therefore, what I'm trying to prove, well, you'll see in a minute, what I'm trying to prove is that all of these guys are 0. And I have that they're small. Okay? Questions? I'm trying to figure out whether I should do these only for the codimension one or not. But anyway. And now I want to do something. Remember one of the conditions of yesterday? So what this basically says is that now I can change what I have is that the distance in B1 of the distance from the plane from X, from Z, to the plane that's the span of EI, I from N to 1 square d lambda, this is less than some epsilon 0 prime. That's what I have. Maybe the plane I started with was not this one, but this implies that I'm close to this one. What I did yesterday said that if I have somebody in this plane, there's no holes. So it has to be close to the span. So if I take epsilon 0 small, so I let eta be small, and I will choose it in a second. For epsilon, for En, there exists a point Z that belongs to the support of lambda such that Z minus En is less than eta. And I am basically done. So bear with me. Here's where we're going. Okay. And what I want to show is that, as I said, so my claim is alpha I is 0 for every I between n plus 1. And m. Okay? Maybe I should tell you why I want to show that before I do that. So let's assume this were the case. If so, Q of x will be then I equals 1 up to n of alpha I xi squared. In fact, I am going to prove a little bit more. I'm not only going to prove that all of them are 0, I am going to prove that all the other ones are 1. Okay? So that's my claim. Let's assume I have the claim. We'll do that in a second. Then this will be exactly this. Okay? And we know that the support of lambda lives inside Q of x minus x squared. Okay, well, that tells me in the sum of I equals n plus 1 up to m of xi squared equals 0. It tells me that the support of lambda lives in the span of EI, I 1 to 1. And I have an n uniform measure that lives in Rn. I never did that, but I talked about that yesterday. It has to be all, the support has to be all of the plane, and it's Lebesgue measure in their modular constant. Okay? So if we prove that all of these ones are 1, and therefore all of these ones are 0. Okay, notice if I prove that each one of these ones is 1, they add up to n, forces these guys to be 0, then we're happy. Okay? Does that make sense? Oh yeah, but you see what alpha I, but I'm going to prove that the alpha i's are all 1s up to here. Okay? And so here I had only 1s. Here I have the sum from I equals 1 up to m. When I remove the first n ones, I only have these ones left. These guys, sorry, these ones are like that. Okay, sorry. Okay. Okay. So that's the only thing we have left to do, to prove that everybody, all of them are. So what's the shortest way to prove that? Assume. So I'm going to assume that this one, remember, they're all, this one is bigger than the next. I'm going to assume that this one is less than 1. I'm going to get a contradiction. If the smallest of the n is 1, and they all add up to n, everybody has to be 1. I'll do that. Okay? So assume, so proof of the claim. Assume alpha n is strictly less than 1. Okay? So remember they're in order. Okay, I'm going to give you a couple of things of algebra. So alpha 1 minus 1 is less or equal than n minus 1, 1 minus alpha n. Okay, and these, actually alpha I, you do it for one and then for the other ones is automatic. For I, 1 up to n minus 1. And then alpha j is less or equal than alpha n, strictly less than 1. By, and this is for j equals n plus 1 up to n. Okay? How did I do this? By looking, I proved this by simply proving that the, remember, the sum of the alpha I 1 up to n is n. Okay, so it's not, there's nothing complicated there. It's pure algebra. Okay. Perfect. So now let's go back to our equation. So we know that if x belongs to the support of lambda, qx minus x squared is 0. Qx is the sum of alpha I xi squared minus the sum from I equals 1 up to m of xi squared. Okay. And so alpha I minus 1 xi squared. Notice that starting at n plus 1, this is, well, at n, but in particular at n plus 1, this is less or equal than 0. So I drop those terms. So I say this is less or equal than the sum from I equals 1 up to n of alpha I minus 1 xi squared. And now I divide into two pieces. And I use that little fact that I wrote there. Okay? So I am going to divide these into two pieces. So 0 is less or equal than the sum from I equals 1, and I erased here something I needed. I have to write it again. I'm sorry about that. Alpha I minus 1 xi squared plus, which I'm going to write into a minus because I want you to remember that it's negative, 1 minus alpha n xn squared. Okay, I haven't done anything, I just, well. Remember what I erased? That's a really good one. Or didn't I not? No, I erased it. Ay, ay, ay. Because of what I had done yesterday, I know that there exists an x that belongs to the support of lambda such that x minus e sub n is less than eta. Okay, so for every eta, for eta small enough, if I choose epsilon 0 small enough, I have this. Okay. Yeah. Yeah. Huh? This is an m, and this is an n. I threw away the last numbers, but it's okay because if you look at it, all of these guys are less than 1, so that was a negative thing. So I threw them away. But I left the last one, which is negative. Okay, and without too much effort, I can choose this x to be of norm 1. So when I look at these, let's do, should we do a teeny bit of algebra? I think so. So when we look at these, out of these we get the following useful information. So what does this mean? Maybe I should expand it for a second. So I'm going to raise it squared. It tells me that x squared plus 1 minus 2x e sub n is less than eta squared. Let's think for a minute. X is close to e sub n. It means in particular that the inner product of x, okay, so this gives you information, x e sub I. Well, x e sub I is x minus e sub n e sub I, and therefore this tells you that x sub I squared is going to be less than eta squared. Okay? I mean, this is. So let's think for a minute. Here, and you can, by seeing, so this is an x. Out of here, you have that x is less than 1 plus eta, 1 minus eta. I'm doing a tiny bit of algebra. What I want to say is that these ones are of order xn squared, and that on the other hand, you can prove that xen is bigger than 1 minus eta. Okay? This comes out of here. Let's plug in that here. This tells you that you have 0 is less than the sum from I equals 1 up to n minus 1 of alpha I minus 1. Xi squared happens to be eta squared. I'm going to remove these, so it gives me, this gives me each one of these. No, let me do it slowly, sorry. N minus 1. These ones, I'm using this thing over here. It gives me n minus 1, 1 minus alpha n. Each one of these is less than eta squared, minus 1 minus alpha n. This one instead, which is this one squared. And if so is 1 minus eta squared. So this is less than n minus 1 squared, 1 minus alpha n, eta squared minus 1 minus alpha n, 1 minus eta squared. And when you organize these, this gives you a 1 minus alpha n, okay, and n minus 1 squared, eta squared, and out of here you have minus 1 plus eta, the minus eta squared I dropped. Okay? So we have these things. Maybe let me put it in a more prominent place. I'm not sure what a more prominent place is here. It gives you n minus 1 squared. It gives you, 1 minus alpha n n minus 1 squared eta squared minus 1 plus eta. So what do we have? We have that 0 is bigger than these for eta small. Okay? Well, this is negative because eta is very small. I have a minus 1. Okay? So this is a contradiction. My contradiction came from the fact that I had assumed alpha n was strictly less than 1. So that tells me alpha n is greater or equal than 1. Which, on the other hand, let's look here. I have these m numbers, m is bigger, that add up to 1. Okay? Alpha 1 is bigger than alpha n, which is 1, which is bigger than. And they all add up to n. Well, this is 1. The other ones better be 1. And the other ones better be 0. And that's what I wanted. Okay? So this proves that the thing is flat. Okay, what on earth has happened? Well, what was happened in the whole story, because, you know, it's like, okay, let's for a minute only think about these measures which are conical. What we have proven is that the conical measures live on the 0 set of a harmonic polynomial, homogeneous polynomial of degree 2. Sorry, harmonic is a different work. Of a homogeneous polynomial of degree 2. This polynomial is not any polynomial, it's a polynomial that is related to the geometry of lambda. Think what this polynomial does. This polynomial is measuring corresponds to how far from being a plane you are. Okay, that's the magic. Had I cooked up another polynomial, or had they cooked up another polynomial, this would have been useless. But the second moment is encoding how far, at least for flat measures, how far from being flat you are. And so that's how you're able to obtain for these, for the conical measures. So let me take, so this doesn't prove the whole theorem. It proves what I had stated, that if phi is n uniform, and n is greater or equal than 3, and phi satisfies double star epsilon 0, their lambda, the tangent measure at infinity, is flat. How do you prove it for n equals to 1 or n equals to 2? You do the same thing, you just are a little bit more careful. It's easier. You only, in alpha 1, if you know that the sum of the alphas has to be 1. You assume alpha 1 is less than 0, you do the same thing, you're done. And the same thing happens for 2. Okay, I don't want to go into details. Okay, so what are we missing in order to say honestly that we have covered everything in Price's work? What Price really wanted to say, for the condition that I called start yesterday, the one that told you if you're n uniform and you're close to flat in this L2 sense, that you're flat. Not your tangent at infinity is flat, but you are flat. We still are missing something. Let's do something. Let's not think that we understand the big picture. Let's do these as you will do the first time you attempt something. Before you understand the big picture, you go through the steps of a proof, or at least I do. And maybe it's a mistake, but I only understand the big pictures by understanding the details, as one of these. Different people think differently. Let's go to the steps of the proof and see what fails for the general uniform measure. Okay? What was about lambda that allowed me to do this? Okay, so do I have it on top still? No. So I'm going to do it here. So everything, so we did this computation. So if okay, so if phi is n uniform, what we proved was that the support of phi was included in the following polynomial. And what allowed us to prove whatever I proved today was the fact that this guy disappears for lambda. So you agree, if for a uniform measure this guy were to disappear, then you're done. Okay? Because the flatness that I had for, it's included here. So if this guy disappears, so the bulk of the section of the section 3 of Price's work, which I think amounts to 50% of the paper, amounts to proving that when you have an n uniform measure, in fact, this guy is 0. So how does he do that? This is a philosophical explanation. This is not a technical explanation. I will be unable to give you a full detailed technical explanation. What did we do here? We computed the first moment and the second moment. What Price basically does, and his moments, these first and second moment do coincide to his first and second moments, but he has more general moments. So philosophically speaking, what he does is the following. He looks at the first, the second, the third, and the fourth moment. Okay? He proves a relationship. So what the third moment is a trilinear form with some properties. The fourth moment is a fourth linear form, with some properties. Has to do, in some sense, with the curvature of this guy also, of the support. He proves that there is a relationship between these first moment. So think of it. This is measuring how far from flat you are. He proves that there's a relationship between the first moment and the trace of the fourth moment. Okay? It's a miracle, but he does that. And then, and I should say the two trace of the fourth moment, which makes it into a quadratic form. And then he proves it for measures that are more general than uniform, but in particular for uniform measures. And what he needs is the growth of the measure at infinity, how the measures of walls grow. What he proves is that this trace somehow has a sign. And it turns out that you have proved before that it had to have the opposite sign. Therefore, that trace is 0 for the fourth moment. And therefore, the first moment, which is controlled by that, is 0. So what he proves, with a huge amount of work, is really a huge amount of work. He proves that this is not here. And then you saw the argument. Okay? So that will conclude the proof of Price. As I said, and I'm going to take 2-3 extra minutes, as I said, the reason I decided to do these and not talk about something that maybe is a little bit, either closer or newer is because I believe there are lots of ideas here that have not been exploited. That is an intimidating paper and that possibly bad publicity has made it more intimidating, but there are ways to read it. And so hopefully what I have done in these 5 lectures is provide a way for you to go and look at it more carefully. Of course, I hit some piece, but now if there's only one scary piece rather than many scary pieces, then hopefully you will be able to do it. I would like to point out, so how did I get into this? I got into this from PDEs. Okay, so I was trained in GMT. I took a detour into pure PDEs. And what happens in the type of PDEs I was looking at? I was looking at boundary regularity of the Dirichlet of boundary regularity of solutions of the Laplacian, if you want, on non-smooth domains. Okay, on very non-smooth domains. To prove anything about that, you focus on the harmonic measure, which is a measure. Every elliptic second-order operator has a probability measure associated with it. For the Laplacian is the harmonic measure. The harmonic measure is a measure on the boundary that tells you what's the probability that if you start a random walk at a point inside, you will first hit a point on the boundary in a given set. And so all the information about the regularity of these solutions is translated into the regularity of this measure, okay? This probability measure. What we prove initially with Koenig is that if you have a domain that is nice in some sense, but not in any conventional sense, the harmonic measure behaves well. And what we wanted to understand is the inverse problem, namely, or the free boundary problem. If you have a domain, and this is, you see this in lots, you have a domain, and you know that all the solutions to a nice operator have very nice boundary properties, can you say something about the geometry of the domain? Okay, you think of the PDE the other way around. What did it mean to have nice properties? It meant that for this measure had nice properties. They were not related to the properties of price because we couldn't assume that, and that's not actually a nice property from the PDE point of view. Okay? The fact that the density exists is not a nice PDE property. PDE doesn't care about that. There were other properties, like good doubling properties, which I mentioned once or twice. And it was like that, by doing blow-ups or pseudo blow-ups of these measures, that we landed on the n-uniform measures. And then we have used the technology of price and some of the ideas of the paper to produce results about regularities of free boundaries. So I know it seems to completely come from a different place, but what I just wanted to say is that this technology can be applied in free boundary regularity problem to give very precise descriptions of your free boundaries. Okay, so that's one of the places where this has been used. I won't say anything else because it's time, but thank you very much.